Alrighty, off to chapter 20. The good news as we dive into yet another chapter, you'll see that's very, very similar, a continuation of a theme from chapter 17 and 18. So, let's do it. First things first, the outline. Outline for chapter 20, we start off pretty basic, pretty slow, good review, I think, as usual, some good review of thermodynamics. And then we go through a variety of reactions. Again, the good news is a single mechanism for the most part, plus a review of some things you've already learned before. So, like I said, more review, more reinforcement. So, one of the first things we're going to review is nucleophilic substitution. Other than acid-base, proton transfer, this is the very first reaction you learned in OChem. And what about SN1 and SN2? Well, SN1 and SN2 were all about leaving groups. So if we have an electrophile that has a good leaving group on it because there's a polar bond, what we know is that some nifty nucleophile can come in, be attracted to the delta positive on that electrophilic carbon, and kick out the leaving group. But what we also know then is that we need to think about the thing that's kicked out, our leaving group, and the thing that's kicking it out, the incoming nucleophile. Because it stands to reason that it would be just as easy for the reverse reaction to take place. And so thinking about equilibrium and reversibility is going to be a pretty constant theme in chapter 20. But right now what we want to think about, what we want to focus on, is looking at leaving groups in general. In other words, why is it okay for my nucleophile to kick out Cl minus, but not kick out CH3 minus? Well, it's really thermodynamics and stability. And if we think about a nucleophile like OH minus, which is a pretty standard nucleophile, we know that this is very, very, very strong base, very unstable. This is a good, strong bond. So pretty much there's no way that this reverse reaction is going to take place. So ixnay on that. So we can kick out leaving groups, but they have to be good leaving groups, aka a good leaving group meaning a weak base, meaning stable. It's stable with its pair of electrons. Alright then, what does that have to do with the next two chapters? Well, what distinguishes the next two chapters from chapter 17 and 18 is this guy right here. Basically, we now look at carboxylic acid derivatives, amides, esters, anhydrides, etc., all of which have a leaving group on there, as opposed to aldehydes or ketones, which are not good leaving groups. So the first step in the mechanism for 17, 18, and 20 and 21 is the same old, same old. We have our incoming nucleophile, and it could be negative, it could be neutral, and it does what we expect it to do, attack the electrophilic carbon and kick the pair of pi electrons up onto the electronegative oxygen. This tetrahedral intermediate is kind of the be-all end-all of the next two chapters. Well, actually it's the be-all end-all in the chapter 17 and 18 as well. It's just that in chapter 17 and 18 it wasn't an intermediate, it was your final product. So now that we have this tetrahedral intermediate, what's different? Well, what's different is that we now have a leaving group. And so we're happy to kick out that leaving group, there it is, and substitute that leaving group for my incoming nucleophile. So this is referred to as nucleophilic acyl substitution, or Carty refers to it as nucleophilic addition. Right here, here's the addition part. Elimination, here's the elimination part because I lost Lg minus. That is the mechanism for the next two chapters. Now, just to hammer the point home, the leaving group equals something that has a reasonable chance of leaving. Yes, we've said in the past that hydroxide and alkoxide are not good leaving groups, but they're good enough, as we've seen in the aldol, they're good enough when it means we're regenerating a strong bond like the CO double bond. So, if the leaving group is a hydroxide, that means you're starting with a carboxylic acid. If the leaving group is an alkoxide, we're talking about doing these reactions on an ester. This is the leaving group that we see if your starting material is an anhydride. This is from an acyl chloride. This is from an amide. In other words, these are all carboxylic acid derivatives, as I mentioned on the previous slides. Alright, so we can get this addition-elimination mechanism to work just fine with a little help if we're using these, if we have molecules that have these leaving groups. What will not work is aldehydes and ketones. In other words, aldehyde you cannot add to get a tetrahedral intermediate and then kick out H-. No. You cannot add a nucleophile to a ketone, get the tetrahedral intermediate, and then kick out R-. No, no, no. Will not happen. Don't go there. So, your mantra for now, for this couple of chapters, is up, down, and out, where this is the up. Up go the electrons on the oxygen. The electrons come back down and kick out the leaving group. And that's it. Alright, so the last two chapters were not up, down, and out. There was no out to it. And that's because we have the aldehyde and the ketone. And we do not, will never, repeat after me, we will never, ever, ever, ever kick out H- or R-, because that would be a very bad thing to do. Very unstable. Alright, so the example that Carty starts off with is transesterification. And this is just the name for the reaction when you're starting with an ester and swapping out one alcohol for another. So, here's our example. Here's our starting ester, whatever it happens to be. We'll call it ester 1. And we're adding a different alcohol. Let's say this is ethanol. Alright, so my ethanol molecule is going to come in, up, down, and out. We're going to kick out methanol, and we've got ester number 2. Now that's an abbreviated mechanism. It's not the correct mechanism. So we'll go through the correct mechanism in a minute. But basically what I want you to focus on is for transesterification, or pretty much for any ester, what you can think of is synthetically, if you have an ester or a carboxylic acid derivative, you want to start thinking about how there is a logical disconnection that I can add this as a nucleophile, here it is, to something some carboxylic acid derivative that has a leaving group that wants to be kicked out. We'll have much more on this in this next mini lecture. So that is your synthetic mantra. Your mechanistic mantra is up, down, and out. Your synthetic mantra is, hey, I can cleave any carboxylic acid derivative right there between the carbonyl and whatever that potential nucleophile / leaving group is. Alrighty. So how does this happen? How do we know this works this way? How do we know that the real mechanism is that this comes here, kicks that guy up? We do absolutely, positively are certain that we get a tetrahedral intermediate, and then we are absolutely certain that the tetrahedral intermediate collapses to kick out the initial leaving group, and that initial leaving group subsequently in the workup or from your other alcohol picks up the proton to give you your final products. How do we know this happens? Prove it, dang it. Well, in the proving, dang it, part, the proof comes in experimental data. We know from the rate law, the kinetics, and from the fact that this is an equilibrium where we can figure out the equilibrium constant, and from the stereochemistry, from all this experimental evidence, we have proof that this is in fact the correct mechanism for this reaction. This is all encapsulated in the energy diagram, so here's an example of some really good review. So looking at the specific example in the upper right hand corner, we're going to take methyl benzoate, add isopropyl alcohol in the presence of a little bit of isopropoxide, maybe sodium isopropoxide, and we're going to get this transesterification going from one alcohol, well, that was pretty poorly circled, one alcohol, one alkoxide to another. Alright, so here we go. We are going to look at the energy diagram, and if we're starting with our starting materials here, our first ester and our sodium isopropoxide, that should be a very endothermic first step, because what we're doing is we're going from an extremely stable CO double bond to, a really remarkably unstable intermediate. Carbon-oxygen bonds are strong, but they're not that strong. A carbon-oxygen double bond is really strong, but not these single bonds. And I've lost any resonance stabilization I had in my starting material. So, bottom line is, this is a very high energy intermediate. Alright, now we're going to do the down and out part of the mechanism. And when we do that, what should the energy diagram look like? Well, before I even tell you about that, let me just highlight these data right here. That darn CO double bond is super strong, and you just killed it and made a lousy CO bond to replace it. So, not the greatest. Alright, next step, the out part. Well, it makes sense that it should be exothermic, but here's the thing I want you to pay particular attention to. It makes sense it's exothermic because I'm regenerating that CO double bond, and that's my rock. But pay particular attention to what we're comparing here. We've got an ester and an alkoxide that I can compare to an ester and an alkoxide. Well, that means it makes sense that these are basically at the same energy level in our reaction diagram. So, the other thing we want to point out on the energy diagram is that this should go lickety-split. Okay, so our delta G double dagger for the second step is teeny, right? So this is fast. This is our rate determining step. It's slow. And the fact that this is, like I said, pretty much even Steven in terms of energy levels means, we're gonna have to figure out some way to make this equilibrium reaction favor the products. Well, Le Chatelier comes to the rescue, as we will see as we plow through chapter 20. All right. So the kinetics is also reflected from this. Again, experimentally determined. What we can tell is exactly what the mechanism supports, although we derive the mechanism from these data. But yes, that rate determining step involves both the isopropoxide and the starting ester. So that supports the mechanism. And the equilibrium constant, which we again determine experimentally, shows that the products versus the starting materials, concentration wise, when equilibrium is reached, pretty much the stability is equivalent and our equilibrium constant is approximately 1. So again, in order to get this reaction to go to product, we have to go and force it to product by using Le Chatelier's principle. All right, so this is an important reaction. Transesterification is the reaction behind the manufacture of biodiesel. So this is a particularly interesting fatty acid, not a fatty acid, triacylglyceride, aka a trilipid, if you will. This is expressed from algae. And what you can see is these fatty acids have a boatload of unsaturation in them. But they're still suitable for use in making biodiesel. The point of the biodiesel here is that you're taking something that you've expressed from soybeans, or in this example, algae, or maybe seeds, nuts, things like that. And then you transesterify them so that your methanol comes up, down, and out to give you your 3 moles of fatty acid methyl ester, aka FAME, and your byproduct is glycerol. So there's the other alcohol portion of your triester. All right, so that's the wrap up for the introductory mini lecture for this chapter. And I was thinking about this, and I wasn't sleeping well. I got up just trying to understand all this, and I got up and looked at the sunrise, and then you know what? It dawned on me. Get it? It dawned on me? Okay. I hope things are going well. See ya.